So far, every test that we've had to determine whether a series converges or diverges has been a series that has positive terms. Both the integral tests, the direct comparison test, and the limit comparison test have assumed your series have positive terms, and you need that in order to apply those tests. In this lesson, we're going to talk about some series that are alternating, and they have some terms that are negative, and the positive-negative behavior exists in a very sort of particular way. So an alternating series is a series whose terms alternate between positive and negative. Here are a few examples. So the sum from n equals 1 to infinity of negative 1 to the n minus 1 over n. So let's just list what the first few terms look like. If we input 1, we have negative 1 to the 0, which is 1, over 1 will be 1. If we input 2, this power is now positive 1, so negative 1 to the positive 1 is negative 1. So we'll have minus a half. Inputting 3, that power is now an even number, so we'll have plus a third. Then the pattern continues, minus a quarter, plus a fifth, minus a sixth, etc. This next one, instead of the first term being positive here, the first term is negative. It'll be negative 1/2. The next term will be positive. It's positive 2/3. And then negative 3/4, positive 4/5, etc. And a series is alternating if there is this flip-flopping happening in the signs. Now it turns out it's actually pretty easy to determine if an alternating series converges. So the first thing that must be satisfied is that bn plus 1 must be less than bn. So in this notation, you have some negative 1 to a power and some bn. The fact that that's negative 1 to the n minus 1 actually isn't very important. In this case, it just means that our first term will be positive, and our second term will be negative, and our third term will be positive, and we're going to use that to do the proof of this. But it doesn't matter if that's negative 1 to the n or negative 1 to the n plus 1. What matters is that they're alternating. So two things must happen. The part of the terms, not including the negative sign, those terms must be decreasing. So the bn are decreasing, getting smaller, which you may have to prove using a derivative. And also, the limit of those terms is 0. Then the series is going to converge. So this is best explained with a picture. Okay, so suppose you start at 0 and your first term is positive b1. So you start at 0, you go over to somewhere where that b1 is. And that is actually your first partial sum S1. And then from that point you take away b2, but b2 is smaller in magnitude than b1, so you do not go all the way back to 0. And so there's your second partial sum. And then you add on b3, but b3 is not as big as b2. So you go over to some value, and there's your third partial sum. So that's adding b3. And then you take away b4, and that's your fourth partial sum. And you can see that these even partial sums are kind of marching up to something, and the odd partial sums are marching down to something. And they're both going in the direction of your actual sum S. If you added on another term, you'd end up over here, and that would be your fifth partial sum. Took away another term, that'd be your sixth partial sum. Okay, and so that is the general idea of why this series is going to be converging. The even partial sums, S2n, approach S from below, and the odd partial sums, S2n plus 1, those approach S from above. So the things you have to do to show a series is converging by this test is just establish that those two conditions are met. All right, determine whether this series is convergent or divergent. So in this case, the part that we're calling Bn is the 1 over n component. So first thing is note that the limit as n goes to infinity of bn, that's the limit as n goes to infinity of 1 over n, that's 0. I know that was the second thing given in the test, but it actually is best to check that one first. It's also the easier one to check. Now the next thing you must show that bn plus 1 is less than bn. And here's how you do that. You know that n plus 1 is bigger than n. So 1 over n plus 1 is less than 1 over n. And 1 over n plus 1 is bn plus 1. 1 over n is bn. So thus the sequence of bn's is decreasing. And you can say that this series converges, and I'm going to abbreviate this test as the AST. And the kind of interesting thing here is that this series is awfully similar to the harmonic series, except for it has that alternating business going on. And the harmonic series diverges, but this series, when you add in the -1 to the n, converges, which is pretty interesting. All right, determine whether this series is convergent or divergent. So let's let bn equal 2n squared over 6n squared plus 1. The limit as n goes to infinity of the bn's will be the limit as n goes to infinity of 2n squared over 6n squared plus 1, which is 1/3. And as that's not equal to 0, this series diverges. That technically is the test for divergence, but you can also say that the second condition of the AST is not met. All right, much like the integral test, it is not obvious that these terms are decreasing if you have variables in both the numerator and denominator. So we're going to have to use a derivative to prove that part. But before we do that, let's make sure that the limit of those terms is 0. So first note that the limit as n goes to infinity of n squared over n cubed plus 1. The way to prove that's 0 is to divide the numerator and denominator by n squared. That becomes the limit as n goes to infinity of 1 over n plus 1 over n squared. And now it should be pretty obvious that the denominator keeps getting larger. Your numerator is 1. This will go to 0. And then we're going to let f of x equal x squared over x cubed plus 1. To show that n squared over n cubed plus 1 is decreasing, we're going to use the derivative. So then f prime of x is low derivative of upper minus upper derivative of lower all over lower function squared. So that'll be 2x to the 4th plus 2x minus 3x to the 4th. Which is 2x minus x to the 4th over x cubed plus 1 squared, or x times 2 minus x cubed over x cubed plus 1, the quantity cubed. So for series, we only care about positive x's because we are only adding up positive these things when there are positive n's plugged in. So this will be less than 0 if this term, that 2 minus x cubed, is negative. And that is true so long as your x is bigger than the cube root of 2. If that is true, your terms are decreasing. Okay, so this means that if we said that bn was equal to n squared over n cubed plus 1, the sequence of bn's is decreasing. And since both conditions of the AST are met, this series converges. All right, here we have cosine of n pi over n squared plus 1. So first we have to confirm that this actually is an alternating series. So let's think about cosine and we'll see what happens as we plug in n like different values of n. So we'd have cosine of pi, which is -1. Then we'd have cosine of 2 pi, which is 1. And then cosine of 3 pi, which is -1. So we do have an alternation going on here. If the terms don't alternate exactly, it isn't an alternating series and you can't use this test. This will be -1 to the n, because our first term is negative, all over n squared plus 1. So in that case, what we're calling Bn is 1 over n squared plus 1. Okay, so test first, the limit as n goes to infinity of the Bn's. That's the limit as n goes to infinity of 1 over n squared plus 1. That's obviously 0. The second thing we have to show is that Bn plus 1 is less than Bn. Well, n plus 1, the quantity squared, plus another 1 is certainly bigger than n squared plus 1. So 1 over n plus 1 quantity squared plus 1 is less than 1 over n squared plus 1, or b sub n plus 1 is less than b sub n. So thus, this series converges by the alternating series test. Okay, this series, well, let's first define the Bn's. We'll let the Bn be e to the 1 over n. So check first condition, find the limit as n goes to infinity of those Bn's. So as n goes to infinity, this 1 over n is going to go to 0. So technically what you're using here is the fact that you do e to the limit as n goes to infinity of 1 over n. That limit moves inside the e function, and we get e to the 0. And don't fool yourself, that isn't 0, it's 1. So thus, this series actually diverges. Okay, well the one with just e to the 1 over n diverge. Let's try this one. So -1 to the n, n e to the n. So first we'll define the Bn's as n e to the negative n. Note that's the same thing as n over e to the n. So first thing we should check, find the limit as n goes to infinity of n e to the negative n, which is the same thing as the limit as n goes to infinity, n over e to the n, which is an infinity over infinity limit. So I'm going to apply L'Hopital's rule, but first I'm going to change those n's to x's. I agree that's a little bit silly, but just deal with it. Okay, so the derivative of x is just 1. The derivative of e to the x is e to the x. So that limit is indeed 0, so we have that condition met. Okay, so for condition 2, to check that this is a decreasing sequence, well, let's let f of x equal, I'm going to use x e to the negative x. We're going to need to use a derivative. An inequality here is just, I won't believe you if you just write down the inequality. I don't believe you understand. So the derivative here is 1e to the negative x plus x times the derivative of e to the negative x is negative e to the negative x. So that's e to the negative x times 1 minus x. Well, e to the x is always positive, and e to the negative x is also always positive. This expression will be negative, or less than 0, if x is greater than 1. And so that means that the Bn's are at least eventually decreasing. And so then this series converges. By the AST. All right, determine whether the series -1 to the n arctangent of n converges or diverges. Well, let's let Bn equal arctan of n. So first thing we should check is find the limit as n goes to infinity of those Bn's. And by now, I hope that I've brought up arctan enough that you just have figured out what it looks like. So arctangent has horizontal asymptotes at positive pi halves and negative pi halves. And it looks approximately like this. So as n goes to infinity, arctan of n goes to pi halves, which is not equal to 0. So thus, this series diverges. Now it turns out that for alternating series, it's actually also pretty easy to estimate the remainder. So here's what this says. If you have a convergent alternating series where you have this inequality satisfied, I just used a's instead of b's, so if you want to be consistent, that would be b to the n plus 1 is less than or equal to b to the n, so we're sorry about that. Then the absolute value of the remainder, and evolved by approximating your sum s by an nth partial sum, is less than or equal to that next term that you left off. And notice that what I mean by that is not including the negative part of that term. So what explains this the best is that picture we drew to prove this test in the first place. So here was 0, over here was S1. To get there, we added some B1. And then from there, we took away B2, and that was our S2. Then from there, we added B3, and that was our S3. And then we took away B4, and that was our fourth partial sum. And somewhere in the middle lived that S. So if we approximated this thing, so suppose our approximation was S4, and we want to figure out, well, what distance are we off by? As in, what is the absolute value of S minus S4? Well, that is this distance here. And notice that that's less than or equal to, if we added our next term on, we just shoot a little bit past it. That'd be our B5. It's less than or equal to B5. And that pattern will always be true. If I had given you S minus S7, that would have been less than or equal to the 8th term. So that's it. So in general, the general formulation is that the distance between S and S sub n is less than or equal to S sub n plus 1 minus S sub n, and that's equal to Bn plus 1. So what that's saying is that the distance between here and here is less than or equal to the 5th partial sum, in this particular example, minus the 4th partial sum. So approximate this sum, a factorial, by using the first 6 terms, and then what is the error in this estimate? So once again, I don't want you to actually get a common denominator. So S6 would equal, okay, let's just list those terms. First we plug in 1, we have negative 1 to the second, so that's 1 over 1 factorial, minus 1 over 2 factorial, plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial. That's about equal to 0.63194, approximately. And from this remainder theorem, we know the absolute value of our remainder is less than or equal to Bn plus 1. So in this case, we have the remainder with n equals 6 is less than or equal to the 7th term, and that is 1 over 7 factorial. And the amazing thing is that by only adding up 6 things, this 1 over 7 factorial is 1 over 5,040, which is about equal to 0.000198. So we only had to add up 6 terms to be within that much. So that's the biggest error we have made using this approximation. I mean, you have 10 terms and you're going to have amazing accuracy here. All right, show that this series is convergent. And then how many terms do you need to have the error less than a really small number? And it turns out that it's actually not very many. So let's let Bn equal 1 over n to the 6th. So first thing is that the limit as n goes to infinity of 1 over n to the 6th, that's obviously 0. The second thing is that you need to show Bn plus 1 is less than Bn. Well, n plus 1 to the 6th is bigger than n to the 6th. So 1 over n plus 1 to the 6th is less than 1 over n to the 6th. So we just established that. So therefore this series converges. And we know that the absolute value of the remainder is less than or equal to 1 over n plus 1 to the 6th. And that's because this is the expression for Bn plus 1. We want that to be less than 0.000123455, and then a 5. I'm going to multiply the n plus 1 to the 6th. I'm solving this inequality. I'm going to multiply the n plus 1 to the 6th over. 1 is less than 0.123455, then a 5. N plus 1 to the 6th. Divide by point, lots of zeros and a 5, and we have 200,000 is less than n plus 1 to the 6th. Take the 6th root, and we have 7.647 is less than n plus 1, or 6.647 is less than n. So that's our boundary, and we must add up a whole number of things. So our n must be bigger than or equal to 7. It only takes 7 terms to get this accuracy. All right, so with this particular example, we could actually solve explicitly for what n is equal to. In this example, we're trying to approximate this sum correct to 4 decimal places. We're not going to be able to find out what it's exactly equal to. So first of all, 4 decimal places of accuracy means you want your remainder to be less than 0.1234 and a 5. Okay, and we know that the absolute value of Rn is less than or equal to Bn plus 1. And in this case, our Bn's are 1 over 2n plus 1 factorial. Be a bit careful here. When you input n plus 1 for this n, you're going to have to put it in parentheses. Okay, so that Bn plus 1 is equal to 1 over 2 times n plus 1 plus another 1, all factorialed. Or that's 1 over 2n plus 3 factorial. And we want that to be less than or equal to 0.1234 zeros and a 5. Now there is no explicit way to solve a factorial, so I'm going to move the factorial over. 1 must be less than 0.00005 times 2n plus 3 factorial. Divide by the 0.00005, and we have 20,000 is less than 2n plus 3 factorial. And there's no explicit way to solve for n, so at this stage you have to just test values for n until you get the first one that works. So when I tested n equal to 2, because it might not actually take very many numbers, when I plug that into 2n plus 3 factorial, I get 4 plus 3, or 7 factorial, which is 5,040. We established that some other time, so that's not big enough. When you plug in n equals 3, though, you get that 2n plus 3 factorial is equal to 69 factorial, which is humongous. It's 362,800. So that's big enough. So we just need n equal to 3. And one thing to keep in mind is we now know how many terms we need. The question also asked us for an approximation. So the approximation is S3, it's the sum of the first 3 terms. So when you plug in 1, we have negative 1 over 3 factorial. When you plug in 2, we have positive 1 over 5 factorial. And when you plug in 3, we have negative 1 over 7 factorial. And that's about equal to negative 0.158.